In this video we're going to be looking at radioactive decays and the ionising radiation that can be produced from these decays, and hopefully by the end of it we will have described how different decay modes occur and look at how they change the nucleus, and secondly we're going to be looking at the properties of the ionising radiation emitted from the nuclear decays. We're going to be looking at three modes of decays initially. The first one is called alpha, and we're going to be looking at two different types of beta decay, one called beta minus and the other called beta plus, and finally we're going to be looking at a gamma decay. And although this very rarely happens on its own in nature, it's usually always associated with either a beta decay or an alpha decay. Okay, the first kind of decay we're going to look at is an alpha decay. They usually happen in really large nuclei, and in order to be able to make the nucleus more stable it will emit an alpha particle. So if we have a look at this, we've got an isotope of polonium, polonium-211, and in this diagram we've got the red particles are representing the protons, the grey particles are representing the neutrons, and we can see here that we've got a representation of the alpha particle, which is made up of 2 protons and 2 neutrons. The diagram and the graph specifically down here is we're dealing with the energy levels of, essentially we've got a collection of alpha particles that make up the nucleus. This blue line is representing the potential energy, and the red line is representing the total energy in the system. And as you can see, the total energy of the system, it remains constant, and the potential energy, it's very low inside the confines of the nucleus, and then it's high, but then it gets smaller as we increase in distance away from the nucleus. Now the nucleus is unstable and it wants to drop itself into a lower energy state. Now this can happen if one of these alpha particles can get on the outside of the nucleus, and then it will just be repelled away from it as the strong force can no longer hold it in and bind it to the nucleus. And if we can see from this graph that in order for that to happen, I'm going to have to increase some potential energy before to come out of this potential well, so then it can roll down the slope and escape away. However, in reality, because this is a quantum system, there is a finite probability that this particle here can just appear on the other side of this potential well, and if that happens, then the strong force has let go and it will accelerate away, and we can do this without having to increase the energy up in the first place. This is a process known as quantum tunneling. So in a moment I'll set the animation running. As you can see, I've actually done it 1, 2, 3, 4, 5, 6 times already, and each of these decays has happened at a different time. So if we set it running, one of the major facts about, or most important facts I want you to appreciate about a radioactive decay is that it is impossible to predict when the atom is going to decay. It's completely random, and we'll come back to this point in a future video. So it happens, and notice, well, it's decayed into lead-207, and now the energy of this nucleus is much lower, so it's a stable nucleus. And if we reset it again, here's the polonium. And there we go, and it's decayed. Now what we're going to have a look at doing is describing the reaction we just saw in the animation in a decay equation. So our initial nucleus was polonium-211, and if you look up on a periodic table you'll find that the proton number of polonium is 84, and we saw that it decayed via alpha, which is 2 protons and 2 neutrons, so it has a nucleon number of 4, and it decayed into a nucleus of lead-207, which has got a proton number of 82. Now, this is quite a simple reaction in order to be able to do it, because if we look at the proton numbers, beforehand we had 84, and after the reaction we have 84, and the same with the nucleon number. To begin with we had 211, and afterwards 207 plus 4 is 211. So a more general way of expressing an alpha decay is if we take a nucleus of proton number Z and nucleon number N, it will decay via an alpha particle. Again, the alpha particle is always 2 and 4, and it will then decay into another element. Let's call that element D, and the proton number of D is going to be Z minus 2, and the nucleon number of D will be N minus 4. So N minus 4 plus 4 will equal N, and Z minus 2 plus 2 will equal Z. Right, we're going to move on and have a look at our second mode of decay. This is the beta minus, where we're going to look at a carbon-14 atom, 6 protons and 8 neutrons. It's an unstable configuration and it will undergo a radioactive decay. Now, I'll click play. One thing to notice, as with the alpha, it's completely random and you can't predict when it was going to go. If we reset the nucleus, we'll have another go. So that one went off just before 5,000 years. This one's taking a bit longer. Hopefully it's not going to take too long. There we go, and it comes off. Notice, each time this decay happens, 2 particles are being ejected from the nucleus. You've got the blue one, which is an electron, and there's a little green one, which is another fundamental particle called an anti-neutrino. So once again we'll do that. See, one more chance for it to happen. There we go. Okay, if we now come back to the board. So again, if we have a look at how this decay mode happened, what we did, we started off with a carbon-14 atom. This underwent a beta decay, call it a beta, and a beta particle is identical to an electron, so we can say that this has got a proton number of -1 and it has a nucleon number of 0. Now, the proton number and the nucleon number have got to be conserved, so if we've got 6 on this side and we've got -1 on this side, our new element is going to have a proton number of 7, and here we've got 0 as the nucleon number, and we had 14 to begin with, so we still must end up with 14 nucleons, and if you look upon your periodic table, that will become nitrogen. And also we had this strange particle which was an electron flavor anti-neutrino. Now, the reason we have to have the anti-neutrino coming out is because the beta particle, which is an electron, these two are both classes of particles called leptons, and leptons' number has to be conserved. To begin with, in the beginning of the decay, we haven't got any leptons here, so if we're producing a lepton over on this side, we need to also produce an anti-lepton over on this side. Now you might ask why we're not producing a positron, but one of the other conservation laws we have to hold on to is charge, and if we were to produce a positron, then we would overall be now more positively charged on this side of the reaction than on this side of the reaction. Because if we look at that, we've got what's happening here is a neutron is turning into a proton, so we're gaining an extra positive charge. So if we're gaining an extra positive charge, we must also gain a negative charge in order for the charge to remain constant. So the only other type of lepton we can have which doesn't carry charge is the anti-electron neutrino. Now if we were to zoom inside the nucleus, what we would see is that the neutron itself is not a fundamental particle, but it's made up of 3 quarks. And the neutron is made up of an up and 2 down quarks. Now, this is going to decay and turn into a proton. And a proton configuration in terms of quarks is up, up, down. So in terms of the quarks, what's actually happening is a down quark is turning into an up quark. That is releasing a beta particle, which is an electron, and in order to keep the lepton number still at 0, we also have to produce an anti-electron neutrino, and that is beta minus decay. Right, now we're going to look at the second type of beta decay, which is beta plus. So let's get a pen. So beta plus decay. Very, very similar to the beta minus decay, only instead of an electron being emitted, it's now going to be a positron. We're going to use as an example fluorine 18. Fluorine 18 is got a proton, well, all fluorine has got a proton number of 9, and what's going to happen here is one of the protons is going to convert into a neutron. So what's going to happen is the proton number is going to go down, so it's going to turn into 8, and the neutron number is going to increase by 1, so the total number of nucleons is going to remain the same. So this now gives us an atom of oxygen. Now charge has to be conserved, so if I've turned a proton into a neutron, well, a proton is positively charged and the neutron is neutral charged, so I've got to have some positive charge left over, so that's where I create a positron. And again, because lepton number has to be conserved, if I'm creating an anti-lepton, because the positron is antimatter, I must also be creating an electron flavor neutrino in order to balance that part up. And again, if we were to zoom into the nucleus, what we'd see is we are starting off with a proton, which quark configuration is up, up, down, and this is going to turn into a neutron, whose quark configuration is up, down, down. So again, what we're doing is one of these quarks here is, in this case, an up quark is going to turn into a down quark. So the up quark turns into a down quark. That will release the positron, or the beta plus, and the electron neutrino. Both of the beta decays can happen via the weak nuclear interaction, because when you're changing the flavour of a fundamental particle, so in this case an up quark going into a down quark, or in beta minus a down quark going into an up quark, then that has to be the weak force. Now the final kind of decay we're going to look at is gamma. Now gamma, as I said at the beginning of the video, isn't necessarily a decay mode on its own. It's usually associated with either an alpha or a beta decay. So if we just have a look at an example, we've got americium 241, which you'll find in your smoke alarms at home. That will decay via an alpha. It's number 95 in the periodic table. So this will undergo an alpha decay, 2 and 4. Our new isotope is going to be number 93, and that's going to drop down to 237, and that is neptunium. Now this will also release a gamma ray, and what's happening here is inside the nucleus, just in a sort of an analogue to when you were looking at energy levels of electrons in atoms, you have energy levels within the nucleus, and what can happen is as the nucleus drops down to an energy level, a new energy level down here, then a photon can come out, and the energy of the photon will be calculated from Planck's constant, and you can get characteristic gamma photons coming out of radioactive sources. Now we're just going to look at some of the properties of the three types of radiation, alpha, beta and gamma. And what we're going to do is, we've got a simulation here of a cloud chamber. All a cloud chamber is a supersaturated vapour of alcohol that wants to turn back into a liquid, but it can't because it hasn't got anything to nucleate on. But if you shoot ionising radiation into there, then the ions it creates will allow the vapour to form on them, and hence you can see a vapour trail, very similar to the vapour trails you get out of jet engines. Now what we've got going on here, I've got a strontium-90 source, which is a beta minus emitter. So out of here we've got an electron coming out. You might notice here I've got a magnetic field going into the screen. So if we were to use Fleming's left-hand rule, we can see that indeed this will have to have a negative charge, because the current will be coming back into where the source is from. So hence an electron being a negative charge going this way is the same as a positive charge going that way. And you can notice you're getting a small amount of cloud as it comes around, as the vapour condenses on it. I can change the strength of the magnetic field. If I increase it, then hopefully the next time it shoots one, you're going to get a very, very tight spiral of the beta particle as it comes out. And again, if I reverse the magnetic field, now my beta minus, my electron, will spiral in the opposite direction. Another interesting point to notice is that not all of the beta particles are coming out with the same energy, so you've got a variation of the radii of the spirals as they come out. Now if I change my source to an alpha emitter, so here we've got the americium, notice now, even though we're getting very long and we're getting very straight lines and we're getting a lot more vapour coming out, because the americium, or the alpha particles themselves, are far more ionising than the beta particles, so you get a much, much thicker trail. Now, beta particles are charged, alpha particles are charged, so in a magnetic field they should also bend, and they should bend in the opposite way to the negative electrons. But because a helium nucleus is so much more massive than an electron, I would need a much, much bigger force in order to see the curvature. So if I increase the magnetic field, you can now just about see that they are getting a curved pattern. Another point to notice with the alpha particles is that they are all pretty much the same length, so all of the alpha particles are coming out with the same energy. And again, if I just reverse the field, I think it will do it on the next one, the alpha particle should bend the opposite direction, which is what we've got. Okay, if I now go on to the cobalt-60 source, which is another source usually found in colleges, you can see you get a very, very faint vapour coming out, and then we've got, if I make the magnetic field a lot weaker, there we go, so we've also got a beta particle coming out. Now most school sources, the source actually shields the beta, so you don't see that coming through, but then what we've also got is just that very, very faint one coming out, and that's the gamma, and it won't be affected if I increase the strength of the magnetic field. It won't be affected by that, because a photon of light, of course, hasn't got any charge, so it will just continue in a straight line, and you hardly see any vapour forming, so the ionisation power of the photon is nowhere near as strong as the beta particle, and the beta particle's ionisation ability isn't as big as the alpha. So now, just in summary, we just want to look at those properties again. So we've got alpha, beta and gamma. Now the alpha particle has got a charge of plus 2e. The beta, well, we're going to go with the beta minus. The electron has got a charge of minus e, and gamma ray has got a charge of 0. In terms of the mass, well, an alpha particle is a helium nucleus, so this is going to be approximately equal to 4u. A beta particle is an electron, so that's going to be about 1 in 2,000th of a u, and a gamma ray has got a rest mass of 0u. And ionisation, then the alpha particle ionisation ability is very high. The beta particle is somewhere in the middle, and the gamma ray is the lowest of the three. And there we go.